true to display the additional regression statistic. So this is just doing the same thing that I already did here. So now you only have one value, right? So the people know about the trick. You have to click in here, and you have to hold down Control and Shift at the same time. No, you have to highlight these. Highlight the 6 cells. Right, you can get that to display.
Cool.
So it's kind of silly that you need like some kind of video game trick thing to get that stuff to display. You do. And you also kind of need to know what these, where there's no labels there, right? It doesn't tell you where, what the information is, right? It just spits the values out. So you kind of need to know that the top left one is M, the middle left is standard deviation is M, the lower left is R squared, right? And the same thing for this side. And there, like the Harris textbook, for example, goes through how to do that, right? Or goes through the layout. You don't really need those additional parameters for this stuff. So that's the first thing, right? Then I asked you to plot both of them, right? So you can do that. So then we want to calculate the residuals, right? So the residuals are just the calculated Y minus the observed Y. Okay? So how do we get the calculated Y?
From your least squares
Yeah.
regression.
So we have Y equals mx plus b, right? Mm-hmm. We have x, so we can calculate what Y would be. Right? Mm-hmm. So this is just putting the x value in here, multiplying it by the slope, adding the y-intercept, and then subtracting that value from the observed value, right? So that's the residual. So I calculated the residuals for all the data points. The other part of that is to calculate the percent accuracy, right? So in this case, I'm just doing calculated concentration over known concentration times 100, right? So we talked about this kind of last time, right? Some of these are, for a calibration curve, a lot of these are kind of crappy, especially at the low end, right? And then they get a lot better. Mm-hmm. Right? So then I asked you to make a plot of the residuals, right? For both calibration. So to plot the residuals, we can just plot that, the residuals versus the injection number or the calibration standard number. So why do I want to plot these like this instead of in terms of the concentration? What is this? When we look at this calibration curve, right? There's 13 points. Mm-hmm. So these points are pretty spread out, right? And then these points are all bunched up. Mm-hmm. Why is that?
Because they're based on the concentration, not on the which number you just
right.
actually sequence.
So you can, these, there's 4 points within 5 nanograms per mil on the x-axis here, whereas there's 0 points within 5 nanograms because of the scale, right? Mm-hmm. Because it's so if we plotted all the residuals on the concentration axis, all these points would be all bunched up, right? Mm-hmm. And so this just spreads them out so you can see things individually. What we're interested in, right, is what's the difference between our calculated Y and our observed Y, and we want to look at each of those points on their own, right? Not and not have them all bunched up so that we can't tell the difference between the first points. Right? So now you can see what the kind of relationship is with the residuals, where they're kind of consistently really high, right? And then they kind of go down and then back up. So, so you can do that, right? And then you can also, plot the accuracy versus the standard. Does that kind of make sense? So you can also, you'll need to do this for the internal standard, right? I'll kind of have a little description, right? But the assumption is that the internal standard, you're adding a constant amount to each calibration standard, right? And so then you can calculate the relative response and you can do the same kind of thing. Right? The last thing I kind of wanted to talk about.
What?
Go ahead.
Can you go back
To.
So you're doing this external standard residuals calculation based on the peak area, right?
Well, yeah, that's the observed Y.
The internal standard response peak area or the peak area?
I mean, in this case, right, for the external standard, we're kind of acting as if this doesn't exist, right?
So then how do we have a difference of like 4,600 when the peak area is only 249? Is with an R squared of 0.99, is it really that far off?
So, yeah. You'll be able to prove this to yourself.
Is it adjusted for at any point?
Adjusted for.
You adjust for it. I'm trying to think where on the computer you then adjust for this.
What do you mean adjust? Adjust.
Your calculations.
At 3.5 orders of magnitude, right? And so you frequently have this problem when you have this wide range of calibration concentrations.
It switches
From positive to negative.
What, 20
Right,
nanograms?
because this, I mean, part of the problem is this y-intercept is high and positive, right? And so it has this, that's why all these are basically pretty much the same. So, yeah, it's a good question. So the last thing I kind of wanted to, and then I just kind of ask you to kind of explain the residuals versus the percent accuracy, right? Why do the residuals increase with increasing concentration? So, one of the things I wanted to, so here's my external standard residuals, and I don't want to go over too much of the internal standard stuff because I want you guys to have something to do. But if we look at the internal standard residuals, you can see what this does to the lower end, right? The residuals are much closer to zero, right? Which is where we want them to be. And then they start to get big as the higher number is the higher concentration calibration standards, right? So when we're thinking about the whole point of this linear least squares line, right, the whole way that this works is that we're trying to minimize the distance between the point and the line, right? So we're trying to make the square of these distances as small as possible. So what does that mean about which distances are bigger, right? So if you're off by 5% for every data point, where is that distance high in absolute in magnitude, and where is that distance low? So say this is 100 and this is 1. If you're off by 5% here, how far are you off by? 105. If you're off by 5% here, how far are you off by? 5. So, and if this is 1,000, right, and this is 50, right? So the relative errors are frequently the same, right, in terms of your y, your residual, but the absolute value is not, and the linear least squares relationship, the algorithm is trying to minimize these distances. And so what frequently happens is you do a much better job of getting through these points as compared with these points. Which is why the errors or the percent accuracy gets better as you go higher up in the curve. Because the line more accurately represents the higher values as compared with the lower values. Okay. So what I wanted to kind of show is that when we look at the internal standard percent accuracy, we get better as compared with the external standard, right? So here, I'd say all these are okay, right? And then things start to get kind of really wacky down here. Here, they're kind of still wacky, but less wacky, right? So 632% off is better than 2,800%, right? But it's still 600% off. So to address this, you can use a weight where you say, I want to weight, you can use all kinds of different weights, but you say, I want to weight the calibration curve so that it tries to get through these points more than it tries to get through these points. Okay. And so one way you can do that is what's called inverse concentration weighting, right? Where you add a weight so that, and that weight is equal to the inverse of the concentration. So this is given a weight of 1/1,000. This is given a weight of 1/0.05, or sorry, 1/1, right? So the weight here is 1, the weight here is 1/1. Okay. And so you can see that what this does, even though it doesn't change what the residual plot looks like that much, what it does change is the accuracy at the low end of the curve. Right? So now, when we use this 1/x weighting, the percent accuracy at this low end, this point is kind of crappy, right? But down here we're at 80 or 90%, which is obviously a lot better than 600% or 200%. So I'm not going to expect you to do anything with the weighting, if nothing else, because there's not really a good way to do it in Excel. But I just wanted to kind of point out that, I guess, I'm sure that going into Thanksgiving, this is what people were really going to be worried about. That, oh man, it doesn't look like internal standards really work. What are we going to do? But if you were worried about it, give me a piece of mind. Not everybody. Not the same things don't keep everybody up at night. So, questions? Okay, so we have two presentations.